All right, so what we're going to do now is we're going to determine some deflections that happen in a truss using the method of virtual work, okay? And so here's the problem that we're going to try to solve. It says here that members AD, BC, and CD are composed of 6061 T6 aluminum, and they have a cross-sectional area each of 80 millimeters squared. It says here that members AB and AC are cables that are composed of A992 steel with cross-sectional areas of 5 millimeters squared each. It says here, given the dimensions and loading shown in the figure, find, right, A, the vertical deflection of point C, right? Point C is down here. So what you'll notice there is that point C does have a load applied to it, but for at least for part A right here, it goes in a direction that is not the direction that we're trying to define the deflection. Also, we have two different loads happening on this structure, right? So this is a situation where we would have a hard time figuring out what the deflection was in the vertical direction at point C with just a pure conservation of energy technique, okay? So what we're going to do for this problem is we are first going to solve this truss with the actual loads that the truss has in it, right? So these loads, the 2,000 newtons applied at point D and the 100 newtons applied at point C, we need to first figure out what forces do those two applied loads create in all of the members of this truss, okay? So what I'm going to do is get into a piece of software that will help me solve that easily and hopefully relatively rapidly. Okay, and here is what it looks like. All right, so just to review in case you all haven't used this software yet, I had to first put in all the coordinates of all the points of all of my joints. So, that's what these are over here. Actually, I'm going to skip over to the one that says material next, okay? And here I put in the area, cross-sectional area of each of the members, as well as the elastic modulus value that I was able to look up out of the table that's in our textbook, okay? I believe it was 68.9 GPA for one of them, and 200 GPA for the other one, okay? Notice these have index numbers to basically describe what material we have for each one of the members that makes up the truss. I usually do this step first before I go and do this step, where I essentially will connect the dots just by clicking and dragging, right, in order to create all of the members of the truss. And as you do this, it basically will define what nodes that member is connected between, and then it tells you or gives you an opportunity to say which of the materials each member is made out of. Okay? So again, this is probably review for most everyone, but in case you haven't done this yet, that's how this works. All right, this is where it starts to get interesting, is when I get over to the tab that says loads, right? And what we're doing at this point in the problem is we are going to put on the actual loads that the structure really is carrying, okay? And so we had a 2,000 Newton load at joint 2 up here. I guess on the figure that was joint D, okay? Since it's downward, I put it in here as a negative 2,000. We also had a rightward load of 100 newtons. Since it's rightward and kind of the presumed coordinate system that's built into this thing has rightward as positive and upward as positive, I put that in as a positive 100 so that it's going right, okay? I also have defined which of the joints are doing the support, right? And so this I defined as joint 3, and how I set this up, that was joint A in the original picture that we had, and that one has both X and Y constrained, whereas joint 4 down here, which was joint B in the original picture, has only the Y direction constrained. Excuse me, only the X direction constrained. Okay, after putting all that in, we can quickly go in here and we can get the results in terms of how much load each of these members has to carry. Notice that member, in the original picture it was member AD, right? It's this one up here, carries 0 load, okay? Why would that be? Remember, we had a vertical applied load happening on that joint 2, right, which was joint D in our original one. If you imagine doing a free body diagram at that joint, all of that vertical load that's applied goes into the vertical direction of force that happens in this member. If you did a sum of forces, let's say, in the horizontal direction, at least, you know, before this thing had its, you know, exaggerated deformation that's showing right here, you would find that this other member wouldn't have any load happening in that, on that joint. All right, well, what do we do with these numbers? Well, I tell you what, I'm going to go into the beginnings of a little spreadsheet right here, okay? What we're going to do is we're going to take those loads and we're going to put them in this column right here, okay? Also, we need to evaluate the length of each of the members in the truss as well. Some of these are pretty obvious, right? Like member CD. How long is member CD? Right, 3.6 meters. How long is member AB? Okay, that's going to be 3.6. I'm going to do like something like equals 3.6 plus 4.4, something like that. Oop. Plus, that's not it. 3.6 plus 0.8, which gives me 4.4. Okay. All right. Any other ones that are easy? DA. Okay. That one's 1.5. All right. Now we have a couple that aren't quite as easy, right? BC is the first one I have right here. How do I get that? Basically Pythagorean theorem on this little member right here. So I would do square root of 1.5 squared plus 0.8 squared. And then similar kind of thing for this member AC, right? So equals square root of, here we're going to have 1.5 squared plus 3.6 squared. Okay, so that gives me all my lengths, and I won't bore you by going and trying to transcribe all these numbers right here. I have another one set up here where we now have those values that I got by basically solving this truss and coming up with those loads, right? And I've also put into my sheet here, kind of preloaded, the amount of cross-sectional area that I have for each of the members BC, CD, and DA, right? Those are all 0.00008 square meters, and then you know, 0.000005 square meters for the cables. So all that's preloaded, as well as the modulus of elasticity values. With all this put in, what do I need to do here? What's my next thing that I need according to this spreadsheet? Yeah, so let me go back to my original picture right here. I need to go to steps 2 and 3. Step 2 basically says solve the truss with only a virtual load at the location where we're trying to determine the deflection and in the direction that we're trying to determine the deflection. Okay? So what I'm going to suggest here is that we put an upward load, right? And I'm choosing upward. Why do you think?
Just so we can assume a positive one.
Yeah, this way, if I take upward as positive, right, that's kind of the way we're used to seeing XY coordinate systems, right? So this way, if I end up with a positive number at the end, it says, yeah, you had an upward deflection. If I end up with a negative number at the end, it says, no, it's the opposite of the direction you put that load, right, which would be downward, okay? So we're going to put that upward load of 1 Newton, okay? Now we need to solve that truss where we've removed our original actual loads that are applied to the structure and replace it with just a single load that's in the direction, you know, at the location and in the direction that we want to find the deflection, right? And it's wisest in these cases to use a numerical value of 1, okay? So what we'll do is we'll go back into our software that we were using. What do we need to change? Just the loads, right? I need to remove these two loads, and instead, at joint 1 down here, I need to put in a Y load of 1. That's an upward load of 1 Newton that I'm putting on right by doing that. Nothing else changes, and therefore, once I do that, I can hit my results tab again, and it gives me all of these results. Notice here that there are actually 2 members that are zero force members when I do this one, right? I've got this vertical member right here, as well as that one that was originally also a zero force member. Why are those 2 zero force members? Yeah, think about this joint up here, right? Now we have no loads being applied to this joint, right? No external loads applied to the joint. If we have either an X or Y load in either of these members, they cannot react against the other one, right? You're going to end up with an unbalanced load if you have any load at all. You can tell that just by looking at that upper left joint, right? So that makes sense to us. We only have loads in these members right here. We're obviously using a software solution here. What if you were doing this solution by hand? Would it behoove you to be able to recognize where you have members with zero forces? Because what that does is it leaves you with certain numbers, right, that you'll have to be working with later, that'll end up being 0, and that'll keep you from having to evaluate certain things, right? So just a little tip there. All right, so these numbers right here that I end up with, these are the virtual loads that are happening in the individual members that we have over here. And so I want to copy those into my spreadsheet, okay, which looks like this. So what I did was I just solved that truss, right, and it gave me those numbers. Now, how do I figure out the total amount of virtual strain energy that is stored in the truss, right, due to that virtual load? Right? I use this equation over here. The virtual work done by this virtual load is going to be equal to, right, do equals, it's going to be equal to the load carried due to the virtual load carried in this member due to the virtual load, which is this number right here, times the actual load carried in that member due to the real loading scenario, times the length of that member, 1.7 meters, okay, divided by EA, right, which is just, this is E, okay, tell you what, put parentheses here, this is E and this is A, right? And what I end up with here, this is the amount of virtual strain energy that is stored in this member BC, as a result of putting my 1 Newton fictitious load on there. So far, so good? Now, what can I do now that I've set all that up? Right? I can click and drag. This now gives me the virtual work that essentially this 1 Newton virtual load that I put right here, this is the virtual work that is introduced into the structure as a result of putting on that virtual load of 1 Newton down there. What do I need to do with all that? I need to sum it up, okay? So I'm going to sum all this stuff up, okay? And that leaves me with a certain number of joules of virtual work that was done by the 1 Newton force down here, okay? What else is this number? Okay, this is a total amount of virtual work, which is going to be in joules or Newton meters, right? A joule is a Newton meter. What was our last step that I recommended when we were looking at this stuff? Okay, it says, first we find the virtual strain energy in each member and sum them up for each case, so that's what we just finished doing with our spreadsheet. Step 5 says the deflections for each case is simply the sum of the virtual strain energy, and all we have to do is divide by 1 Newton to get what that is in meters, right? So essentially what I'm saying here is that this value of 0.006392, that is the number of meters of deflection that happens at point C in the upward direction, right? What does the negative sign mean? It means it actually goes downward, which kind of makes sense based on the directions that the original loads were being applied, right? Wouldn't you expect point C to move downward in response to those loads, right? This loading scenario over here looks to me like it would push point C downward. So that makes me feel better there, okay? Now, what do we have for part B in our original problem? It says now for part B, we're supposed to find the horizontal deflection of point C, which means we need to now solve what kinds of loads are in each one of the members of this truss if I put a force at point C in the horizontal direction with a value of 1 Newton. Okay, that's easy to do in this piece of software, right? We just go into the loads, and what do? Just change it and put it in the X direction here, right? Once I've done that, I can look at my results, right? I, again, for the same reasons, end up with 0 force members for these two up here. And then, so I'm left with these values over here. So if I take those and I put them into my spreadsheet, these are what I just found using my piece of software. So what do I need to do here? Basically the same thing I did just a second ago, right? I need to take what is the virtual load that is carried in each one of the members, multiplied by the real load that was carried in each one of the members, multiplied by the length of the member, right? Divide this by E times A. And then I add all that up. So I need this for each one of the members. And then down here, I want the sum of all those values. Okay? This one also turns out to be a negative value. What does that tell me? Okay? I assumed that the virtual load went to the right, came out with a negative number that says it's really moving to the left, right? As a result of applying the real loads that I'm putting on the structure, okay? Now, let me show you something else that's kind of fun. If I go back to the original, loading case, right? If I go back to loads again, and I take off my virtual loads, and I put back on the actual loads that were being applied, okay, which I think was those two like that, and I look at these results, it will tell me in this little app what the deflections are going to be for joint 1 in both the X and Y directions, right? Shall we compare what they came up with versus what we just came up with? Okay. Here is what they came up with in the little app that I was using, minus 2.15 times 10 to the minus third for the X direction. That was this value, right? Minus 6.39 times 10 to the minus third, there's that value, okay? I'm actually not sure what's inside of that little app that I was using to calculate all this stuff. It would not surprise me at all if it was using, perhaps, the method of virtual work inside of it in order to come up with those values, right? It's very possible it's using the same technique that I'm showing you here because it's pretty easy to automate that process for kind of a general purpose truss, okay? So just to kind of close this out, what I want to do is I'm going to snip what I came up with here and drop it into my original problem, right? And do the last little step because I think it's kind of important to do it, right? Okay. The last little step says you take your total virtual work that was caused by the virtual load that you applied, and you divide again by that virtual load. So that if I want to determine what's the delta for point C, let's say in the Y direction, what I have to do with that is I have to take my virtual work that happens in that direction. Okay, this is in joules or Newton meters, and I divide by the amount of load that I had to apply to the structure to get that internal virtual strain energy. That amount of load was 1 Newton. And therefore, this turns out to be negative 0.006392 meters. Right? And the other one works the same way, right? Delta for C in the X direction, we take the virtual work that happened in that direction. So due to the 1 Newton force that we put rightward at point C, so 0.002150, all this is in Newton meters. All this divided by 1 Newton gives me that many meters. Okay? And so it's very easy to see here why, whenever you're applying a virtual load to do this method, usually people like to use the number 1. We can use any value you want. You can put on there, 52.89 newtons or something like that. You do the whole process. At the end, you'll divide out 52.89 newtons, right? And it'll end up giving you the same result as what we got by using 1 Newton. Okay? Questions? All right. Yeah.
So when we applied the virtual load,
Yeah, so his question is, in our case, we ended up putting a virtual load horizontally at point C to do part B, right? And his question was, so even though we already had the 100 Newton there, we ignore that one and do this one instead? And the answer is yes. What you do for each of these virtual loads that you put on there is you remove all of the real loads when you get ready to do the virtual load, even if it's already, even if you have one there that's kind of already going the direction that you wanted to find. Okay? Let me make one last little comment about if you were having to do this problem by hand. Okay? What if you did your virtual loads in all of your members for this problem first, before you found your actual loads? What would you have found? You have found that because we have these zeros here and here, any kind of information that you would have needed to find for members CD and DA is not going to be relevant because they're going to get multiplied. Those are going to be the lowercase n values there. It's going to get multiplied in here and end up adding nothing, right, as far as the virtual work. If you see that early on in a problem that you're working by hand, it prevents you sometimes from having to solve for some of the loads in some of your members. Does that make sense? It works for the other one too, right? Even if you did your actual loads first, right? You put your actual loads on there and you solve for everything. As soon as you see that one of your members has a 0, that we know from the very beginning then that that member is not going to contribute anything to the virtual work. And therefore, any additional effort that you otherwise may have spent on that member, you can not spend it if that helps you, if that saves you some time. Does that make sense? Okay. Why do you think I'm bringing this up? Will you have this tool when you take your test? Okay? But what will you have when you take your test? You'll have your brain. You will have a calculator, right? But your brain is the one I'm focusing on here. Your brain, if you can identify that you've got some zero force members, those become members that you don't have to, and they can be zero force members either for the real loads or for the virtual load that you're getting ready to apply. As soon as you see that, that becomes a member that you don't need to know anything about it anymore. Okay? All right.